everyone, welcome back to Window Seat Studies. I hope you all are doing well. So we were discussing about neurobiology, in which we have learned a lot of things till now. We discussed about the history, where we discussed how the researchers they made the observation and gave certain conclusions about the nervous system and what the nervous system is made up of. Then we learned about the nervous system, the two important cell types of nervous system, the signaling unit, neurons, and as well as the supporting and protecting unit, the neuroglial cells. So, about neurons, we learned about the structural part of the neurons and the types of neurons. We learned how the different parts of the neurons they are associated with different functions while the signal conduction. Then we also learned about different types of neurons based on the different properties that they exhibit. The structure based on the structural properties, what are the types, based on the functional property, what are the types of neurons, and then based on the conductive properties, the fastest conducting neuron to the slowest conducting neuron. So we learned about neurons in those lectures. Then we also learned about neuroglial cells, the different types of neuroglial cells that are found in our central nervous system as well as peripheral nervous system. Then we learned about myelination, how it is different in central nervous system and peripheral nervous system. Then we also learned about the electrical properties of neurons. From the basics, like how the neuronal cell membrane is polarized, and due to the polarized nature of that cell membrane, it exhibits the property of being excited. Okay, so whenever a stimulus arises, the neurons get excited because the cell membrane is polarized. So we learned about the resting membrane potential and how it is maintained across the membrane throughout till when the cell is at rest. And then we also learned about action potential, how it is generated. And in today's lecture, we are going to learn about the propagation of action potential, the different types, the different conduction, the different types of conduction that happens across the axon, the conductions of the action potential. So we already know that the cell, when it is at rest, it has it has a membrane potential which we know call as the resting membrane potential. So when cell it has rest, the inside the membrane part which is on the cytosolic side, it is negatively charged, while the extracellular part of the membrane it is positively charged. Means the membrane, neuronal membrane, is polarized when the cell is at rest, and the membrane potential when cell is at rest, it is known as resting membrane potential. Okay, so once the stimulus arises, it results into opening of ion channels, and that will shift the charge separation, that will reduce the charge separation, means it will cause the depolarization of membrane, reduction in the charge separation, which will cause into the action potential generation. Okay, so let's say that in this particular segment, the depolarization is happening. So the charge distribution that will change. So the membrane is positively charged, but in this particular section, the cytosolic part will get positively charged, while the extracellular part will be negatively charged. So the membrane, the due to the unequal distribution of ions, the membrane charges that will get reversed. The charge distribution will get reversed. So this is how the action potential will be generated. So now the membrane potential in this part, it is known as action potential. Okay, so once this charge separation is disturbed, in the when the cell is at rest, when the charge separation is disturbed, it can result into either graded potential or the action potential. Okay, so this could, if the small deviation in the membrane potential is seen, that is what we call the graded potential, or if the deviation is large, that is what we call the action potential. So we have learned about all those things in previous lectures. Today we will be learning about how the action potential which is generated in this segment, how it is propagated over the long distances. So there are two primary modes of propagation. Okay, the first one is the continuous propagation. Means when the action potential is generated at one point, it travels continuously throughout the axon. That is what we call continuous propagation. And other one is saltatory propagation. Okay, the continuous propagation, this is seen in the unmyelinated axons, the neurons whose axons are unmyelinated, while the saltatory propagation, this is seen in myelinated axons. Okay, so let's see how exactly the continuous propagation happens across the axonal membrane. Okay, so this continuous propagation, uh, this happens in unmyelinated axons, due to with the help of the stepwise depolarization and repolarization. So first the membrane gets depolarized and then it gets repolarized. Okay, so now let's take a look at this part. Okay, so let me just copy paste this part, this diagram, and here. Okay, so see, let's see what happens. So when the now the charge distribution is changed. Okay, so once the ionic distribution is changed, so now we already know that the ion current will be generated. So the ions will flow, like the current will be generated from the positive direction to the negative direction. Okay, so the current flow will be something like this. Okay, so this will be the current flow. So once the charges flow from this direction to like the from positive to negative, the current flow will be from positive to negative. So this will create a small electrical circuit, the small local electrical circuit, which will propagate in this direction. Okay, so now what will happen? Okay, so let's see now what will happen. So once those positive ions, they move from here to here, the current moves from here to here. So the negatively charged extracellular side, it will get positively charged. Okay, and the positively charged intracellular side here will get negatively charged, restoring the resting membrane potential. Once the resting membrane potential is restored in this segment, so let's call this segment 1, 2 and 3. So once the resting membrane potential is restored in the second segment, the first segment will create the charge separation in first segment will change. So now the extracellular side of the first segment will get negatively charged and the intracellular side will get positively charged. So now this first segment is depolarized. Okay, so like in this scenario 1, the segment 1, it is at rest. Okay, so it is maintaining the resting membrane potential. The second segment is depolarized. Okay, so now in this scenario second, the second segments get repolarized, restoring the resting membrane potential, and the first segment will get depolarized while the second segment is restoring the resting membrane potential. So now this is how the current, this is how the uh, action potential will propagate, like the action potential which was generated in this second segment, that is now propagated to the first segment. So this will continue. So now the other segments, they have the resting membrane potential. So now the ion flow will be same from positive to negative, and this is how the action potential will be propagated. So this kind of scenarios are seen during the continuous propagation. So like it will have stepwise depolarization and repolarization cycle as and it happens in the unmyelinated axons. Okay, so each segment of membrane will be depolarized in sequence, so making this mode relatively slow and metabolically expensive, because every segment is getting stepwise, it is getting depolarized and repolarized stepwise. That is why the conduction of the signal will be slow. So the conduction will be slow, and it will be metabolically expensive as well, because it is, it is open. So while restoring the resting membrane potential, you need to activate sodium potassium ATPase pump, and you for when stimulus arises, you are going to open those ion channels. So that is why it will be metabolically expensive, because you will need a lot of ATP for, because the length of the axons is quite long, right? So on the overall length, you have to activate the sodium and potassium ATPase pump, and that is why it will be metabolically expensive compared to what the saltatory propagation is. In this in this saltatory propagation, the electrical signals, they are going to jump. They are going to jump across the myelin sheath. Okay, so the in the continuous, like in the, this is the membrane. Okay, so in the continuous propagation, the charge will, like the current will flow continuously over the length, but in the, because they are unmyelinated, right? But in the myelinated axons, okay, the myelin sheath is kind of, separating segments of the axons here. So myelin sheath. So this is a nerve cell of peripheral nervous system. So the Schwann cell is forming the myelin sheath over the axon. So now the current will, the current will, the action potential will be regenerated at the parts where the myelin sheath is absent, and we call them nodes of Ranvier. So at the nodes of Ranvier, the action potential will be regenerated, and that is why the movement of the, movement of the current will be a jumping movement. From here, the current is going to jump here, here, here. So the propagation will be a jumping moment, and this is what we call as the saltatory conduction of the action potential. So this is due to, myelin sheath acts as an insulator, which prevents the ion leakage and reduces the membrane capacitance. So for the purpose of understanding saltatory conduction, we first need to understand a few things. We need to understand the physics of the of this of this scenario. Let's learn about a few things, like the length constant and the capacitance, and what happens across the membrane, how the myelin sheath, it is able to it is able to result into the faster conduction. So I hope, if you don't know, I hope you have watched the lecture about the equivalent circuit model, in which we compared the neuron with an electrical circuit. So we compared the properties of the neuronal membrane with the components like resistors, batteries, and the capacitors. So if you don't know about that, please revisit that lecture, because if you don't know about it, you won't get whatever I'm trying to explain here. So let's learn about the passive conductive properties of the. Let's learn about the passive conduction that happens in neuron. So passive means you are not going to need any kind of, so here you're not going to need any kind of energy, ATP. But in this case, by passive, I mean the current, okay, the current which is going to die out eventually. Okay, and when does this happen? I know you, I hope you know that this happens during the graded potential generation. Okay, so let's see what happens when the graded potential is generated, and why do the, why do the current dies out. So you must have learned about this in your physics lectures during high school, that whenever a current is generated across a wire, across any object, so let's say across this wire the electrical current is generated. So now this electrical, at this point the current is generated, and it is going to propagate across the membrane, across this wire. So once this travels, it eventually dies out at certain distance. Let's say at this distance, it is going to die out. So once this property of dying out the current is due to the resistance which is offered by this membrane or this wire. Okay, so because the wire has certain resistance due to its radius, due to its length. Okay, and that resistance is going to result into the loss of the ions, loss of the current, and now current which started from here and it is propagating in this direction, it will die out at this point. Okay, so the efficiency of this passive spray, it depends on the two resistive properties. So let's assume that this is a membrane. Okay, so this is membrane of an axon. So the the property that the current, the graded potential which is generated here, which is resulting into the ionic current. So now whenever there is potential difference, V, that is going to result into the a charge flow, right? And once the charge flows, that is what we call current. So a potential difference results into the current flow, current generation. So the graded potential which is generated at this point will result into the current flow. The current will flow from this point to this point, and it will eventually die out due to the resistance which is offered by the axon. So the resistance which is offered by the axon is of two types. Okay, so this resistance, this is of two types. What are those two types? So now the resistance is offered due to the membrane. So the resistance which is offered due to the membrane, the lipid bilayer of the axon, is known as Rm. I'm referring this as the membrane resistance. Okay, but now current is this is not like, this is not 1D. Let's draw it in 3D. Okay, so this is a wire, like axon is a cylindrical structure, right? So this is axon. So in 2D, the current is flowing through this lipid bilayer as well as it is flowing like through this lipid bilayer, as well as it is flowing through the axon, right? Let me just erase this. Okay, so the flow of current is through the wire, through this wire. Okay, as well as it is through the axon as well. So the resistance which will be offered, that will be offered by the lipid bilayer, and that is what we are referring as the membrane resistance. And there will be other resistance which is offered to the ion current which is flowing through the axoplasm, and that is what we are going to refer as the axoplasmic resistance here. So when current flows through the exoplasm, the cytoplasm of axon, the resistance that it is experiencing, that is referred as the Ra. So both of those those resistances, they are going to result into the eventually dying out of the current. So from, let's say, from point A to point B, the current eventually dies out. So there's a equation which gives the decay of the signal. That is what we call the passive signal decay equation. So the passive signal decay, this is given, let's say that this is given by this equation. So Vx is equal to, let me write the equation first, V naught into e to the power x by lambda. So let me explain this equation in detail to you all. So let's say that from the point A to point B, the whatever passive current is generated due to action potential, that is going to eventually die out. So the distance at which it dies out is the x. Okay, so the potential, the membrane potential which is generated at the starting point, the initial membrane potential, when the current starts, it is V naught, and when the current is reduced to zero, at that point, whatever the membrane potential was, it is known as Vx. Okay, so the membrane potential at point A, from where the current is originating, it is known as V naught, and where the current dissipates, the current is 0 now. At that point, whatever membrane potential was, it is known as Vx. Okay, so let me write it here. What are the meaning of those symbols? So Vx is the membrane potential at distance x from the origin site. Okay, so origin point was the point A. Okay, so from in this diagram, from point A, origin point A, to the distance x where the current eventually dies out. Okay, so that membrane potential is known as Vx, while V naught, it is the membrane potential at x is equal to 0, means at the initial point, while x is the distance and lambda is the length constant. Okay, and length constant is a very important property, because it represents, so length constant, this represents distance. Okay, this distance over which the membrane potential Vx, this drops to 37%, means 1 by E times the of the initial value. Okay, so like length constant, whatever the value of length constant, it will tell you about the distance, like from the about the distance x, where the eventually the I is going to be the 0. Okay, so let's say current started from here, it goes 0 to this point, and at the where the this point will be where the Vx will be 37% of the V initial. So here was the V naught. So this is the length constant value. So this gives you an important idea about how the conductive velocity will be. So the value of length constant, this depends, the okay, so it's a very logical thing that it is going to represent the distance over which the membrane potential is going to decrease from the initial value. So when a membrane potential is decreases due to the resistances, and that is why theoretically, or like equation, by equation we represent that the lambda, it depends on the membrane resistance as well as axial resistance, and that is why lambda is equal to the square root of the membrane resistance over the axoplasmic resistance. Okay, because this tells us about the distance at which the membrane potential is going to decrease, and we already know that the membrane potential that is going to decrease due to the resistance which is offered by the membrane. So resistance that is offered by the axon or the neuron, that is of two types, and that is why the length constant, it is given by this formula. Okay, so it is given by the square root of membrane resistance. Okay, so here membrane resistance has unit ohm centimeter. Okay, and the axial resistance. Okay, so, oh sorry, my bad, ohm per centimeter. So this is how the length constant tells us about the property, like about the length at which the membrane potential is going to decrease. So now let's learn about on what this resistance depends. So we already know the resistive property of any kind of object, any wire, any membrane, that depends on the length as well as the area that is offered, the radius of that wire. Okay, so we already know this in high school. So the resistance which is offered by membrane, this is inversely proportional to the cross-sectional area of the axon. Okay, so this is inversely proportional to the pi r square, because this is this membrane is cylindrical membrane. So let's say that the radius that it has, I'm representing it with r. Okay, so r is equal to radius. Okay, so the area will be pi r square. So that is why the resting membrane potential, it is inversely proportional to the cross-sectional area of axon. So this is inversely proportional to cross-sectional area of axon. Okay, well, the axoplasmic resistance, it will be inversely so axoplasmic resistance is offered here, right? So it will be inversely proportional to the circumference of the axon. So what circumference will be? So we know that the value formula for circumference is 2 pi r. Here r is radius. Okay, so that will be inversely proportional to 2 pi r. Okay. So this is how we know that the axon radius, it is going to have important effect. So radius has important effect on the resistances. So we already know that the resistance will be inversely proportional to the radius. Okay, by this formulas. So this is very basic things that we already know in physics. I'm just revisiting all of the concepts so that you can integrate those concepts, those physical properties with the electrical properties of neurons. Okay, so like we are making the analogy between electrical circuits and the neuronal membrane. So we are assuming that the neuronal membrane or the axon, this is basically a wire. This is a cylindrical wire. Okay, and that is why we are going to apply all of those properties that a general wire has, like resistance and capacitance, to the neuron membrane. So now, for till now, we learned that whenever we increase the radius, okay, so whenever we are going to increase the radius of an axon, it will lead to the lower resistance. So once the resistance is low, this means that length constant will also be high. So radius, so the radius of the, so this gives, so the form, so this gives a formula. Again, I'm not going to talk about derivation, how the formula came. So this proves that the length constants is directly proportional to square root of the radius. Okay, so let's list down whatever formulas that we learned till now, so that whatever the next point that I'm going to tell you, that will be quite clear to you all. So length constant is equal to the membrane resistance over the axoplasmic resistance, while the membrane resistance is inversely proportional to cross-sectional area, and the axoplasmic resistance, it is inversely proportional to pi r, and this balance between them gives the length constant, and that is why length constant, it is directly proportional to the square root of the radius of axon. Okay, so now we know that the length over which, so the more is the radius, this will tell us that more will be the conductive velocity. How? So see, whenever lambda is large, this means that the length at which the membrane potential will die out, like current will die out, will be large. So if the lambda is small, the length at which current is going to die out will be low. So this means that whenever lambda is large, that means that the conductive velocity will also be more. This means that the whatever current is generated, it is traveling over the large distances. Lambda is large means the current is traveling over large distances. This means in given amount of time, when we compare the axons with large lambda and the axon with, let's say, axon A has large lambda and axon B has small lambda. When we compare both of the axons, for 1 second, the conduction will be faster in the larger axon compared to the smaller axon, and that is why the conductive velocity of this axon will be higher than the conductive velocity of this axon. Okay, so that is why we can directly say that the conductive velocity of any axon means the conduction of the current the capacity of conduction of the current will be directly proportional to membrane resistance over the exoplasmic resistance, and it will be directly proportional to the square root of radius. Okay, so this is how the the lambda facilitates, the larger lambda facilitates action potential propagation by allowing the local current to depolarize over the long distances, because the resistance whatever resistance offered to the axon, it is less. So that is why when we say that the axons which are larger and thicker, means the radius is higher, radius is also large. So axons which are larger and thicker has high conductive velocity. So uh, whenever you came across this sentence, now you will remember why. Okay, so we already know that the axons which has a higher radius, which are thick, like this axon will have slow conductive velocity compared to this axon. Okay, so why? The reason is this: because see, the membrane resistance which is being offered here is known as Rm, and the exoplasmic resistance will be Ra. So due to the large cross sectional area, both the membrane resistance as well as the exoplasmic resistance will be low, and once both of those resistance are low, the flow of ion current will be over the long distances. So let's say that small deviation in graded potential is generated in both of those axons, but this will travel over the shorter distances, and this velocity will also be low compared to what happens in this particular axon. Okay, so now let's discuss how the myelination, it is helping in the faster conduction of the propagation of action potential. So let me draw an axon here. Okay, so this is an axon, and this membrane is going to offer the membrane resistance, and this is going to offer the exoplasmic resistance. So what happens is that when the membrane resistance is higher, okay, so what results into higher conductive velocity? The high conductive velocity will always be seen whenever the membrane resistance will be higher and the exoplasmic resistance will be lower. Why? See, whenever the membrane resistance is high, this is high. Okay, so whenever this is high, Rm is high and Ra is low, at that point of time, the length constant will be high. Okay, so by the equation, like by mathematically, now you know why the conductive velocity will be high when the resting, like the membrane potential will be higher, like this will provide more potential. I'm drawing thick membranes, means that the membrane resistance is high and the exoplasmic resistance is low. So mathematically, you already know by the equation, you already know that the high membranic resistance and low axonic resistance, that is going to result into the higher value of length constant, and once the length constant is high, means the conductive velocity will also be high. But now let's understand this theoretically, like mathematically you already know, but let's understand it in a different way. So whenever the membrane will be thick, like membrane is offering more resistance, so whatever ion current is generated here, whatever ion current is generated, that will not leak through this. So this, we already learnt in last class that the membrane has ion channels. Okay, ion channels which allows the passage of some ions. Okay, so like when the membrane which has zero ion channels, it has infinite resistance, but due to the presence of ion channels, the membrane resistance, which was infinite initially, gets reduced and becomes finite. Okay, so the whatever membrane resistance is there, the membrane resistance will be finite due to the presence of the ion channels, right? But the number of ion channels will tell you how much resistance is being offered by the membrane. The more are the ion channels, the more are the open ion channels, means the lesser will be the resistance. But we need the higher resistance for faster conduction, because whatever ion fluxes are being generated here, that are producing the ion current, that ion current should not dissipate throughout this membrane. So the, this ensures the higher membrane resistance ensures that whatever current is generated here, when it passes like this, it would not leak through the membrane. Okay, so for decreasing this leaking through, so from decreasing this leakage, we need to increase the RM. Okay. Oh, for so whatever I'm representing this with orange color, for decreasing this leakage, we need to increase the membrane resistance. But we need to lower the axoplasmic resistance, because we need to ensure that the current will flow through this direction. Okay, so we need to ensure that the current flow will be in this direction, not in this direction. So we are inhibiting the current flow in this direction by increasing the membrane resistance, and we are ensuring that the current will flow in this direction by lowering the axoplasmic resistance. So this purpose is served by myelination. So in the unmyelinated axons, the leakage is quite significant, and that is why unmyelinated axons, they show the slower conduction of the ion currents. But in the myelinated axons, myelin sheath, which is produced by the PNS and by the Schwann cell in PNS and by the astrocytes in ANS, that is going to provide an insulation. So now at this point, okay, let me first draw the myelin sheath properly. So here in this particular segments, the membrane potential, the resistance offered by membrane will be much higher than compared to what resistance is being offered in the case 1. So the axonic A, RMA, will be, RMA will be lower than RMB, the membrane potential which is offered in the axon B. Okay, but the axoplasmic resistance is, let's say, the axoplasmic resistance A in case A, and here is the axoplasmic resistance in case B. So both of them will be nearly equal, because the axoplasm is not going to differ here. Okay. So this creates a significant difference due to the membrane resistance of A being lower. The conductive velocity, or lambda A, will be less than the lambda B, and that is why the conductive velocity of the velocity of current flow in the axon A, that will be less than the velocity of current flow in axon B. So this is how so the myelin sheath brings out two changes that is going to help in faster conduction. First, that we saw that it is increasing membrane resistance, which prevents ion leakage, promoting axoplasmic flow of current. Thus, signal transduction will be faster. And the second thing that is done due to the presence of myelin sheath is that the membrane capacitance means the charge storing capacity of membrane, that is decreased. So it decreases the membrane capacitance. So capacitance is the property of any object, is the property by which the object is able to store the charge. So due to this, in the equivalent energy circuit model, I forgot to tell you one formula about the time constant. It is equal to the Rm, the resistance of the membrane, and the capacitance of the membrane. So capacitance of the membrane is decreased in this case. So this increases the time constant, and due to the time constant reduction, the speed of depolarization increases. Okay, so well, let's understand it in different way. So capacitance means the charge storing capacity of the membrane. Okay, so once the charge storing capacity of membrane is decreased, so this means that membrane is not storing charge. So what is it is doing? It is doing the ion flux. Okay, this means that through the open ion channels, the ion is getting so there will be some ion influx or some ion efflux. So this will speed up the polarization. Sorry, the depolarization. So due to the increase in the depolarizing capacity of membrane, the conductive velocity will be high. Okay, so I hope you get it why the myelin sheath increases the conductive velocity. So that is why in the continuous propagation versus the saltatory propagation. In the continuous propagation, this happens in unmyelinated axons, while the saltatory conduction, it happens in myelinated axons. Okay, so myelination, it increases the membrane resistance and it decreases the membrane capacitance. So due to the increase in membrane resistance, ion leakage is prevented. Okay, so there is no ion leakage, and due to the decreasing of the membrane capacitance, this increases the depolarizing capacity of the membrane. Okay, and due to which the conduction will be fast here, and conduction of the signal will be slow here, because in the continuous propagation of action potential, the graded potential will eventually die out. But for maintaining the continuous propagation of action potential, it will need ATP, and that is why it is metabolically expensive, because you need this action potential to be propagated, to travel across the membrane through only depolarizing and repolarization cycles. So this is how the action potential is it travels from one point to the other point in myelinated and unmyelinated axons. So with this, we are done with all of the electrical properties of neurons. We have covered everything so far. So that we covered the two important electrical signals, the graded potential and the action potential, how they travel through the axon and what are their properties. So in next lecture, we will learn about other things in neurobiology. We will learn about synaptic transmission. We will learn about neurotransmitters. So with this lecture, we are done with all of the electrical properties, the resting membrane potential, action potential, graded potential, and action potential propagation. We also learned about the equivalent circuit model in the neurons. So in next lecture, we will learn about synaptic transmission. Till then, see you. Bye bye.